Alright, so our project is Aeronav, where we build a drone from start to finish. Before we get started, I just want to thank all the massive amount of people that came out here to watch us today. It really means a lot to me, Kaushik, and I'm sure to all the other people presenting their Capstone projects as well. My name is Kadhir, Ramesh.
I'm Kaushik.
Alright, and before we actually get started, we're just going to talk about ourselves for a little bit. I am a senior at Grandview High School, and I am committed to CU Boulder. I hope to double major in mechanical engineering and computer science. I've spent all 4 of my years in Grandview in the engineering department, so I've seen these Capstone presentations for a while, and I always wanted to do it on my own. I've done several extracurriculars such as the Technology Student Association, the Future Business Leaders of America, Speech and Debate, SCC, NHS, and a few more. Some classes that I've taken related to this project: AP Computer Science Principles, AP Computer Science A, CAD, and Engineering Design. I also have a few certifications such as the CSWA and the PCAP, which both put me at the associate level in programming in Python and in SolidWorks.
So I'm Kaushik. I'm a junior in Grandview right now, and my intended major when I do graduate is aerospace engineering, probably a minor in business. Right now, the current class load that I've taken, which corresponds to this class, is AP Computer Science A in Java and AP Computer Science B in Python. The extracurriculars I do are DECA, FPLA, TSA, and also speech and debate. My skills are mostly, up to this point, they were mostly computer science related, machine learning, Java, Python, and web development. But in this class, I learned more about engineering, so I could also add that to my skill set. And our project was basically, our goal of this project was to just blend our interests of aerospace and mechanical engineering into some project that we found was worthy of our time, which was a drone in this case.
Alright, so let's talk about project inspiration for a little bit. So like I said, I've been in this engineering department at Grandview for the past 4 years, and I've seen these Capstone presentations for 3 years in a row. And it's always fun to see how people are creative and can apply their knowledge to something that they want to do. And like everybody else, I wanted to do something fun. And one day while I was scrolling on YouTube, I saw this guy named I Build Stuff build a drone umbrella. And this seemed like a fun idea, even though it wasn't really that useful. So me and Kaushik decided, hey, it seems like a fun idea, let's give it a try. And before we talk about how much it changed, we'd like to talk about our project objectives. For one, I wanted to learn how to design products. Like I said, I've been in CAD and engineering design, and I've learned how to use SolidWorks during my time at Grandview. However, most of the products that I've created have been things that have already been designed for me. I've never used my imagination to actually create a tangible product on my own, which is why I wanted to develop that skill. Next up, enhance my knowledge in aerodynamics. So obviously, for a project that is entirely based in the field of aviation and drones, I'll need a good knowledge of aerodynamics in order to do this project. The same goes for electrical engineering, where I'll be soldering a lot of electrical components together and fitting a lot of things together. So I wanted to develop my skills in basic electrical engineering, especially since at the beginning of the year, that was one of the majors that I was considering for college. Improving my project documentation and management skills. So, like I said, I do a lot of extracurriculars, and for all of these, the common problem is that I'm very bad at managing the project and actually documenting my progress throughout the entire year, which is why for this project I wanted to do something different, and I wanted to actually properly document all the progress that I made, and I wanted to make sure that I was managing my time well. And finally, build skills in performance testing. I've achieved all 4 of these project objectives, but this is the one that I struggled with the most, because we actually have to have a finished product in order to do performance testing, and this is why this is the one project objective that I was lacking.
So these are my project objectives. So first one, obviously, I need to avoid procrastination. That's been a huge problem of mine ever since high school. I lack the discipline to do my work on time, so what I hope to get out of this class is to just avoid procrastination, set some weekly goals, and get my work done on a timely basis. The second one is enhancing journal skills. Throughout this class, we have a total of 5 journals with information like research, accomplishments, weekly goals, and my goal is to just use this information to get better at journaling skills that I can use further on in my career as an aerospace engineer in the future. Next one is public speaking. Currently, I'm in speech and debate and I do STEM. And I want to build on top of that skill for public speaking to talk about presentations and my progress with this project. And then time management efficiency. I want to learn how to stick to weekly goals and make checklists in order to meet performance and be productive in my work time. And lastly, it's problem-solving abilities. This is just referring to me understanding how to work on ESCs and flight controllers and other electronics that I might use in the future.
Alright, so how has our project changed? So the thing about the YouTuber that I was talking about before is that he actually made this project and it took him over 6 months, even when he was already experienced in making drones and very experienced in computer science and designing products as well. So we simply didn't have the skills or the time and the money because we would first have to learn these skills in the first place and then apply it to what we wanted to do. In addition, there's money. I designed my own drone frame for just a regular drone, and the quote from PCBWay was over $900. And obviously, I'm not going to spend even more than that on a project for my high school project, which is why we decided to just make a regular drone. And originally, we wanted to implement this with computer vision either way, but our expert advisor, who we'll introduce in a minute, advised us against that because that can be very, very unpredictable. Basically, implementing computer vision into a drone, especially when you don't know how the software works and there's not a lot of resources for the drone flight software, it's very unpredictable. It can take a few weeks, it can take a few months, and it can take a few years even, which is why we decided to just make a regular drone. However, we couldn't do this on our own, so we decided to assemble a team.
So firstly, our expert advisor, who was our advisor with most of this project, we got him first week of November, and he's been helping us with parts sourcing, just finding the right parts and checking their compatibility. We used to email him a lot about the parts we're getting, and he would give us feedback about what parts to use, alternatives for the parts. He also helped us with the build planning. He gave us step-by-step instructions on how to build the drones. We gave him the resources that we found, and he helped us find more resources like documentation for beta flight, and also for the SpeedyB flight controller that we use. And also software recommendations. He recommended Betaflight, ArchPilot, and also PX4. And it's important to mention that he's a final year PhD student in computer science, and he has a lot of experience working with drones. That's why we signed him as our expert advisor. He's very knowledgeable in this field. And he works very regularly with Raspberry Pis and other computing units like Jetsons and Qualcomms, which is essential for our project as computing is the major part of our drone.
He helped us a lot, but there were a few other people that helped us a lot during this project as well. Blake Helker, outside of just this project, even for the past 3 years, he's been helping me out with my public speaking skills a lot. So he's our presentation specialist to help us refine slides, help us polish our websites, and etc. Then we have my mom over here. She's my emotional support. She's always been there for me when I'm feeling stressed, whether it's making me chai or just words of affirmation.
Next up is my dad, Vukanti. He provided us most of the funds to buy the drone, as the drone was not cheap. It costed us about $400 to buy the drone, to buy the components for the drone, so he helped us with that. He also troubleshooted any errors we had with the Betaflight flight control system. And also Jaden John, he's our drone expert. He's built drones in the past before, and he helped us mostly with soldering problems we've had and also with the drone assembly process, as we were not really familiar to this process at the start of the year.
Alright, now that we've got that out of the way, we can focus on the bulk of the project, which is research. We divided this into 5 main components, those being aerodynamics, the drone design and configuration, the electrical and physical components needed to actually build the drone, the assembly, and the software. So first up, we have aerodynamics. There are 3 main forces that act on the drone: drag, which a lot of you may know as air resistance, the weight, and then finally we'll move on to to thrust and how a drone works. So the drag acts opposite to the direction that the drone is actually moving. If you're moving up, then the drag will drag it down, and then if you're moving downwards, then the drag will actually act up. Weight is pretty simple. It's just the weight of the drone, how much the mass of the drone is weighing down the drone, and basically all you need to know is that the thrust has to be significantly greater than the drag and the weight of the drone combined. So now let's talk about how a drone actually works. See these propellers? They displace air. Basically, all a drone does is it takes the air from above it and then it pushes it down. And then the air has an equal and opposite force that pushes the drone upwards, and that force is what we call thrust. And like I said before, in order for a drone to achieve liftoff, the thrust has to be significantly greater than the drag and the weight combined. Next up, we have drone design basics. So there are 6 main different drone configurations for a quadcopter, which include X, H, plus, Y4, V-tail, and A-tail. You don't need to know what all of these means because we immediately eliminated the 3 asymmetrical options, which leaves us with these 3. This right here is the H configuration, and the reason we eliminated that as an option is because it's very bulky and it's not nearly as stable as these other 2 options. So that leaves us with the plus option and then the X option. So the plus configuration makes the control logic really easy, because if you look here, the propellers are in the 4 cardinal directions. So like I said, that makes control logic a lot easier. However, it's not as aerodynamic, because if you pay attention to how the drone actually works, it needs airflow above all of these propellers, meaning that this bulky drone part of the drone frame right here will get in the way of the airflow of the drone, which limits its aerodynamics. This one is much more aerodynamic, and in addition, it's the most popular choice, so a lot of softwares are actually optimized for this X configuration. And that's why we eventually decided that we wanted to go with an X configuration for our drone. Alright, now let's talk about some of the physical components that we need to actually build a drone. The flight controller, which I'll be calling FC, is basically just the brain of the drone. It takes signals from the radio receiver, which is this green motherboard looking thing right here, and it takes those signals and transmits it to the rest of the electrical components in order to tell them what to do. The most important electrical component other than the flight controller is the electronic speed controller, or the ESC. Now there are 2 different types of ESCs, a 4-in-1 ESC and these individual ESCs that you can see on the diagram right here. So the most important thing to realize about these ESCs is that they are very different in how they work, because 4-in-1 ESCs usually come with the FC as one single unit. And so what this means is that you don't need a power distribution board. So normally when you have 4 separate individual ESCs, you need a power distribution board because you need to distribute the power evenly to every single one of those ESCs. However, when you have a 4-in-1 ESC, since it's a single unit, it already has that internal power distribution implemented into it. And since it's directly connected to the FC, it's much more efficient as well, as the signals travel much more quicker from the FC to the ESC. So basically, we bought a FC ESC 4-in-1 unit because that eliminates the need for a power distribution board, and it's much cheaper as we don't have to buy 4 individual units for the ESC. Alright, let's talk about some more physical components. The radio receiver, I briefly mentioned this in the other slide. This receiver right here gets soldered onto the FC, and that allows the FC to receive the signals from this radio transmitter, which is used by the user in order to basically tell the drone exactly what to do. The propellers, the size and pitch of the propellers are the main 2 factors that affect how the drone flies. If you think back to my earlier explanation on how a drone flies, it displaces air from above it and then basically just pushes it downwards. So looking at the size and the pitch is the distance that it moves forward in one rotation without slippage, which basically just means if you screw it into a solid surface like wood, how far into the wood would it go in one single rotation? That is what the pitch is. So the higher the pitch is, the more air it displaces in one rotation, and the higher the size is, the more air it displaces in general, which means a higher size and pitch is better for more stable drones that have higher thrust, and for agility and speed, lower size and lower pitch is better. Finally, we have batteries and their naming conventions. This 4S right here stands for the amount of cells that are connected in in series. And the amount of cells that are connected in series determines the voltage of the battery. This 1500 mAh stands for milliamp hours, and that is essentially how, that's like the capacitance of the drone, or in other words, how much charge the drone's battery can actually hold. This 130C is the C rating, which essentially means it's like a capacity multiplier. So you multiply it by the capacitance, and basically that tells how many amps it can discharge at a single moment.
So next up, let's talk about one of the main risks we had when we were building this drone, which was the possibility of a short circuit. A short circuit is basically the movement of current through an alternating path that of least resistance. And this is basically a shortcut through the path this is a shortcut through the wrong path, essentially throughout the ESC. And as a result, short circuits can fry the ESC board or the flight controller, and this usually happens due to solder bridges, which is basically a phenomenon that happens when a solder connects 2 different ports of an ESC, which are not supposed to be connected. This is most common on the motor pads and also the power pads. So throughout this, let's talk about the different types of soldering mistakes that could happen that could eventually cause short circuits or several different electrical problems. The first one is cold solders. This usually happens when the solder is not hot enough and results in the solder being uneven shape, and this results in weak or inefficient connections between drone components. The next one is a solder bridge. This is basically where the solder connects 2 different pads of the ESC or flight controller that are not supposed to be connected. This results in the ESC enduring a circuit that's not meant to withstand. As a result, as the current passes through the ESC, it fries the components within it, causing the drone to be useless, basically. Next up is the overheating of components. This usually happens when the soldering iron is way too hot, and this results in precipitate forming over the flight controllers from burn solder. Also, this can also lead to lifted pads, which is when the solder pad completely comes off the flight controller, and this results in the flight controller being useless and needing us to buy a completely new one. And also, let's talk about the connections between the radio receivers and some other components like the flight controller, for example. The ELRS flight receiver is the one that we use for this specific project. And the receiver is basically a mediator between the transmitter, which is the controller, and the drone. It sends signals between the both. It helps with communication. The ELRS receiver has three main wires. They're for signal, power, and ground. They all correspond to their own pads on the flight controller, which is R2 for signal, 4B5 for the power, and the G for ground. If they're connected in the incorrect spots, it could cause incorrect signals to be transmitted between the receiver and transmitter, causing the drone to either not fly or malfunction. Next up is a connection between. Next up is a connection between the power wires and the ESC. The power wire is typically a red positive lead, which connects the VBAT pad on the ESC, which is the positive pad. We also have a negative ground pad, which connects to the black lead. Next up. We also explored three main types of software based on advice from our expert advisor, which is Betaflight, ArchPilot, and PX4. Each of them have their own strengths and their own unique capabilities, so I'll talk about those now. Firstly, we have PX4. PX4 is a professional-grade autopilot system. It's usually meant for industry-standard drones that require automation and professional efficiency. This drone requires several different components like a Pixhawk flight controller rather than the SpeedB flight controller that we have currently. It needs a GPS module and also a barometer and telemetry radios to help it communicate with the computer rather than just the transmitter. But the benefits of this software is GPS navigation, so you can set predetermined flight paths and it will follow it. And also it has autonomous flight using different types of computer vision libraries. But the thing about this software is that it's extremely time-consuming to learn. There's practically no documentation for this software, and it only works on Linux, which means we have to change our operating system on our computers to help make it compatible with our drone software. As a result, it's too bulky, requires too much knowledge about this flight software, and adds too many unnecessary parts that weigh down our drone, which requires speed, agility, and hyper-performance. Next slide. The next one is ArchPilot, which is similar to PX4. It's also an automation software that helps with creating drones that are automated, and it has a lot more selections for vehicles like drones, boats, Land Rovers, and even planes. This also requires a Pixhawk flight controller rather than the SpeedB, as it helps with autonomous flight. And due to this, it also requires a GPS navigation module and telemetry radios, which add up in price too. We estimate that the total overall price of these external parts could cost upwards of $400, which completely ruins our budget for this drone, which we planned on for about $450. As a result, it also causes the drone to be way more bulkier and increases the weight, and thus demands more load from the propellers, which have to increase the thrust. Next slide. Thus, we decided on Betaflight. Betaflight is another open source firmware, but it's more for racing drones and freestyle drones rather than automated flight drones. It doesn't require a camera or GPS module, and it's solely just a manually controlled drone software. The benefits of this is flight stability, reliable performance, and real-time control over your drone. It also has a feature where you can configure the drone through a smartphone app, through the SpeedB app or the Betaflight app, so you can do configurations and test it outside without needing to connect to your computer, and it supports Bluetooth mode as well. It works perfectly with our SpeedB flight controller that we have, which is a SpeedB F405 V4 controller, which is extremely reliable and performs really well on drones. So therefore, we decided on using Betaflight as it works on the mobile apps. It has compatibility with our drone parts. It's really easy to configure, and it's built for performance and for flight stability.
Alright, so next up we have our timeline. This was made when we were extremely inexperienced. We had no idea what we were doing, and we still needed to do some more research and basically figure out what we were doing. So, like I said before, this was really unrealistic compared to our adjusted timeline. And basically, I wanted to have most of the research done and the entire drone design and all the physical components ready by December. And then I would actually build the drone in January and just assume that Kaushik would be done with all the computer vision stuff. And then I would move on to doing comprehensive flight tests. So since this was extremely realistic, we made an adjusted timeline that actually reflects what we did. So I severely underestimated the amount of research that I would actually need to do during this project. The entirety of the first 2 months were mostly spent on doing a lot of research on drone parts, aerodynamics, and the different configurations of a drone like I explained before. And I also familiarized myself with Fusion 360 because I chose that as my CAD software for designing the actual drone frame. Next up in December, I researched a lot more about drone design, and then I made a list of electrical components for me to order in order to actually assemble the drone frame when second semester came. Then January and February was finalizing the drone design and then gathering all of my physical components and just fitting everything together. And then these last 2 months have been focused on polishing up the website, finishing up the build, and making the final presentation.
So this is my original timeline. Mainly for my original timeline, I was focused on just learning about drone control softwares, learning about machine learning softwares, microcontrollers, and just testing the functions. So I divided it up into 4 different sections. So October through November is mainly my research period. This is where I aim to learn more about C++, which is the coding language you use to code drones. Also, I plan on learning more about machine learning and object detection. December was mostly the implementation part. That's where we decided on buying. That's when we planned on buying components for our drone, like the motors, the ESCs, the flight controllers, and all the frames and stuff. January through February was our tuning and testing phase, where we planned on making the drone, testing it based on different environments, testing the code to see if the machine learning software would work. And then March through April was just our final presentation month to get ready for this presentation. But this was extremely unrealistic, as the machine learning part itself would take longer than the building of the drone, which is what our expert advisor advised us, as the training process would be extremely long in the scope of this project. So this is our adjusted timeline. October through November was still the same, as we had the reflection of changing up our drone project around. December-ish, that's when we met with our advisor, and he advised us not to do the machine learning part, as there's practically no documentation or projects done before that incorporate those principles onto a beta flight drone. So December is when I learned even more about beta flight and PX4 and ArchiPilot, since we needed to use those either way. And then January and February is when we got all the physical components, we assembled them, and we did all the flight testing, and we flew it even. Then March through April is when we assembled the complete drone with the frame, with the battery pack, the radio receiver. We configured everything. We finished up our presentation and our website.
All right, so let's talk about some of our accomplishments. For one, we achieved most of our project objectives. If you go back to the first few slides, I reflected on my project objectives and talked about how I met 4.5 of them out of 5. And then we did finish a drone build, which was the final goal after we adjusted our entire project. And then we flew the drone, crashed it, and then we gained the opportunity to build it again because it broke. So yeah, that was pretty fun, and we probably are going to work on this in the future. We're going to fix the drone once this project is done, and then after that, he might even take it into his Capstone class next year and start implementing the computer vision like he originally planned. All right, so that was our presentations, and now we will have time for questions. Colton?
Who crashed the drone?
Both of us.
Yeah, I flew it into a tree and then he flew it into the concrete, so it's a equal contribution. You were there?
So I assume that this current drone didn't have any sort of GPS stabilization or anything like that?
Well, it had some basic PID tuning, but that just comes default in beta flight. We didn't actually configure anything like stability related on our own. It's more so just what was already included in the software, and then he was the one that configured the software itself.
In the future, would you consider adding GPS stabilization and all that, or is it
Yeah, for sure. Something that we actually did look into was having a GPS and maybe like an RTH function, which means like return to home, or we could just have a different predetermined flight path itself. That's a bit harder to do on beta flight, which is why we did look into RDPilot and PX4 as well. But yeah, that's just some other things we were looking into.
Currently on beta flight, I guess if you're doing a manual flight, the GPS isn't really necessary. That's more for autonomous flight. So if you're controlling it manually through the transmitter, then the GPS really isn't necessary. But if I want to implement like the computer vision libraries next year, yeah, that's when it's going to be more helpful for me. Yeah, Kevin.
So I noticed you guys were a group of two. How well were you able to split the workload between you guys?
So can you say that again?
He asked how well we were able to split the workload between the two of us. So honestly, I think it wasn't too bad because like I was doing the drone design from the beginning. So for the entire first semester, I was contributing a lot. But because he ended up learning a lot about machine learning and computer science, he helped a lot more in the second semester than he did in the first. But at the end of the day, we both gained valuable experience and learned a lot of stuff about what we want to go into for our career in the future.
Any more questions? Yeah.
So do you have any kind of, say you run up like GPS to like your cities like Kadhir, do you have any kind of like inertial system or is it all just manual control?
There is the accelerometer that helps us maintain a stability and make sure it's at a level angle. But that's about all we have. We could install like a barometer to measure the height of the drone to make sure it doesn't like crash involuntarily. But yeah, that answers your question.
Will you ever use the drone once it's done?
Oh yeah, for sure.
Really?
Yeah, I mean, like we said, one of our support advisors, Jaden, he also is a drone expert and he's built drones in the past. We might do some racing with him, or we might like, I don't know, make a video about like our progress, you know, so we can keep documenting things as we work on the drone in the future.
You should add a camera on it.
Yeah.
That could be something we could work on later. We could add like a camera and maybe some yeah, just a camera setup to make sure it's like more comprehensive and like a complete drone build. Yeah, are you?
Were you guys able to measure how fast the drone runs before it crashed?
No, because honestly, there wasn't really like a way to like measure how fast it was. We didn't have like a radar gun or whatever to like measure how fast it went. So honestly, yeah, we decided, we're guessing maybe like, I don't know, how fast we could
I don't know. I don't really care. It's broken either way.
go. Yeah. You have an opportunity to fix it.
Okay.
Do you know why the drone crash was just poor flight controllers?
Yeah, so it's just a lot harder to control than it seems. It's like learning to drive a car. That's the easiest way I can put it, in a way that other people can understand. The throttle's like extremely sensitive. Turning's really sensitive as well, and it's not exactly intuitive, because like a car, you turn the wheel one direction and then it moves in that direction. A drone isn't the same way. You have to like figure out how to control it in the first place.
Like when you're programming the drone, you have to do a bunch of test flights to make sure that you're tuning it right. Honestly, it crashed on the first like flight, so we weren't even able to like adjust the tuning and do the PID tuning, so that's why it was so sensitive and that's why it crashed. Any more questions? Yeah, are we?
Were you guys able to brainstorm how you could attempt it to be more user friendly?
Like what do you mean?
Like you were saying that like some for example.
Yeah.
Throttle's a bit sensitive only due to the fact that the motors were also like really powerful in relation to like how powerful the motors were.
Yeah, I mean, something else we could do is also reduce the thrust of it by changing up the propellers, because like I said before, propellers can increase the thrust a lot, and the pitch on this drone specifically is really, really high, which means that it displaces a lot more air in one rotation than it does than other propellers, even of the same size do.
The drone itself is extremely light compared to all other drones of similar build, because we're missing a lot of parts like the GPS module, the camera setup, and on top of that, we're using the motors that are around 80% power. So it's a lot of power and not a lot of weight. So it's like it moves really fast and it's really hard to control. If that makes sense. Any more questions?
George?
If you wanted an umbrella drone originally, why did you make your current drone so much more touchy, like hyper maneuverable?
Can you say that a bit louder, please?
If you wanted to originally make an umbrella drone, do you really need to make it so maneuverable and agile?
Well, if you were listening, you might have noticed that we didn't actually build an umbrella drone. We ended up changing the project a lot, and we just made a regular drone. It wasn't supposed to be the same size at all. So, yeah.
All right, thank you.